Good day, viewers. My name is Darlington Okoka, and I welcome you to Delwit Electrical YouTube channel. Today, we shall be talking on the basic fundamentals of electrical circuits. As we all know, electrical systems involves circuits or involves the use of circuits. So in this episode, we'll be talking of the current, the voltage, and resistances. And these are the fundamentals of electrical circuits. So as electrical engineers or scientists, as we know that every electrical system has the fundamental possibilities of generating, transmitting, and distributing. So these are the three fundamentals, and it's also applicable to electrical circuits. So in our electrical circuits of today, we're going to be seeing how voltages are being generated from the source point and taken through a transmission system to our load point. So in what we're going to be discussing today should be summarized into four fundamentals. We're going to be talking about the generation of electrical energy. We're going to be talking about the transmission of the generated energy. We're going to be talking about the application, that's the distribution of electrical energy. And finally, we're going to be taking how to control this electrical energy. So we're going to be taking you to our circuit. And in this circuit, we're going to be showing you the basic fundamentals of what is obtainable in these three systems. So on my screen now, what you are seeing now is for V1. V1 is our source voltage. So the source voltage is actually where the voltage is being generated from. It could either be your normal battery system, it could also be your generators, or anywhere powers are being generated from. But for basic circuits, it's usually your battery system. So you could use any simulation softwares like the Multisim, the Pro Tools, the Livewire, whatsoever. But I'm using Circuit Wizard on this my system now. Then we have the switch. The switch is the control. So from this source you are seeing now, the voltage is being released and current is being flown from this source down to this. These are wired now. It's like our transmission system. Then this switch is the control. So on this control, the moment you turn on if you turn on this button, that means you are making it a complete circuit. Then from this complete circuit, it moves down to your load point. So what generally is from your basic transmission system, this is your circuit also has the fundamentals. So this is our generation, this is our transmission, this is our control, and this is our distribution. So those are the four basic things we have in electrical systems. Having analyzed these circuit theorems, or this circuit that distinguishes the generation, transmission, distribution, and control, we are going to define some basic terms. There are four basic terms we'll be defining, because if you know these four basic terms, it serves as the fundamentals of your learning process of electrical circuits. If you miss these fundamentals, every other circuit analysis you are going to be doing is going to be a problem. So first and foremost, we'll talk about the electrical charge. Electrical charge is an electrical property of an atomic particle of which matter exists. Matter is anything that has mass and occupies space. So definitely it is measured in coulombs, and we usually represent it with Q. Atom itself is made up of three basic fundamental blocks. We have the electron, we have the proton, and we have the neutron. Electron is the negatively charged particles in an element, and is usually represented with 1.6 times 10 raised to power 19 coulombs, of which is equal to the proton, but in terms of magnitude, but is positively charged. So proton and neutron has 1.6 times 10 raised to power 19. The electron is negatively charged, while the proton is positively charged. But by the time we have equal quantity on an element, we have equal proton and we have equal neutron, is neutral. So in that case, our neutron is neutral. It has no charges. So invariably, we can now say that our charge is measured in coulombs, and our charge, which is represented by Q, is directly proportional to current. So Q, the equivalence, the constant between the charge and the current, is our time. So for every time t, our Q is directly proportional to I. So that's why in the equation of charge is Q is equal to IT. So that's going to serve our first fundamental equation in electrical engineering. The second one we're talking about is electrical current. Current is the rate of flow of charge, and it is usually measured in amperes. and the symbol we have agreed, or it has been agreed to be represented with is I. So from the formula now, the rate of flow of charge, that means our I is now equivalent to change in Q over change in T. Now, current we know must or usually flows from the higher potential to the lower potential. So from our circuit, as you can see on the screen, this is our voltage source. So current now will flow from the higher potential down to the lower potential. But we know that electron is the opposite, it flows in this opposite direction. So when the electron is flowing, electron flows in this direction. So we've been able to define what current is measured in change in T over R. That means 1 amperes is equal to 1 coulomb per second. From our formula for current, which is I is equals to change in Q over change in T, it shows that current needs to be changing. It needs to be changing, and that is why we have the two types of current, alternating current and direct current. So the moment the current is changing, it has a sinusoidal movement. So on the graph, as you can see on the screen, on the graph you see that we have a sinusoidal graph. It's changing. So when it's changing, it's called the alternating current, and this is the current that we use to power most of our appliances at home. Your TV, your refrigerators, your ceiling fan, all this makes use of alternating current. But the moment the current is constant, the current from one position to the other is constant, it's not a sinusoidal. Your graph showed a constant flow. That is direct current. So usually most current we see from our sources of voltage, for example the batteries, is direct current. You can see this is the graph for the direct current, and this is the graph for the sinusoidal current or the AC alternating current. So what we have actually said, obviously, is basically for current is for current to flow, there must be a complete. First of all, there must be a complete circuit. That means current must flow from the voltage source down to the load in a complete circuit. And 2, there must be a force that is making that voltage to flow, and which is called the electromotive force, or the PD, the electromotive force. That means the source voltage must be complete or must be charged in that circuit. So those are the two basic things that is expected for current to flow within a circuit. So the third term we're going to be explaining today is the voltage. The voltage is the energy required to move a unit charge from point A to point B. As can be seen on this circuit now, you will discover that the voltage between point A and point B, the voltage between these 2 points is our VAB. So from our formula now, our VAB is the energy required to move the charges from this point here to this point here. That is why our VAB now will be equivalent to change in W, which is your energy, over change in Q, which is your charge. So our voltage is measured in volts. So that means 1 volt is equivalent to 1 joule per coulomb. So there are various other formulas. So by the time we start talking about Ohm's law or other laws that come, there are other formulas that we can use to define our volts, our current, our resistance, and other parameters. But for these our fundamentals, we now know that our V from point A to point B, which is VAB, is equal to change in W over change in Q. Having explained what voltage is and the potential difference, we will now try to use this circuit to explain one fundamental term that has to do with voltage, the electromotive force. Now, if you look at this circuit, you would see that the source EMF, which is the electromotive force, represents the driving influence that causes a current to flow. So the current that is the driving influence that makes a current to flow through this direction is the electromotive force. But note that the EMF is not a force in general, but it represents the energy expended during the passing of a unit charge through this source. Therefore, the EMF and the PD looks at the potential difference looks similar. But however, EMF is always active in that it produces an electric current in the circuit, whereas the potential difference may be passive or active. It is usually passive when it has no tendency to create current in a circuit, but it's active when it creates current in a circuit. So with what we are seeing now, this EMF that is producing current in this circuit, so obviously it's active. But by the time we remove this EMF and we have a passive equipment, then obviously it becomes passive. So this is generally what voltage definition, EMF and PD is all about. So we'll move to the fourth item, which is resistance. This fourth item, resistance, we shall extensively discuss on this when we are talking about Ohm's law. But resistance is the opposition to the flow of current. That means when current wants to flow in this direction, it increases the resistance that it will make it flow in the opposite direction. So the opposition to the flow of current is what is usually known as resistance. So when we are discussing Ohm's law, we are going to be talking about how voltage is in proportion to current, and the constant between them is the resistance. So when we get to Ohm's law, we shall talk extensively on the calculation that requires resistance. So, but our fifth term we are going to be analyzing today is power. Power is the time rate of expending or absorbing energy, and it is usually measured in watts. That is, in the general formula now will now be our P is equal to change in energy over time. So let's see how we're going to discover our electrical quantities in terms of power. Now, when we say our P is equal to the W over the T, where P is our power, the W is our energy, and Y our the T is their time, usually in seconds. Now, we will discover that from our previous formula, we know that the W over the Q, if we use the W over the Q, which is the rate of energy to charge, and the Q over the T, which is the rate of charge to time, we'll discover that our dW over dQ dot dQ over dt, when dQ cancels dQ, what we are left with dW dt, which is equivalent to P. So, but we know that the W dQ from our previous formula is V, and the Q dt is I. Obviously, our P will not be equivalent to VI, which we all know that voltage times current gives you power. So in this, we've been able to establish our 5 fundamental principles summarily. We are now saying that our charge, which is equal to Q equal to IT, is one of our major formulas that we are going to, fundamental formulas. Then our current is the rate of charge to time. So our dQ dt is our current. Our voltage is the rate of flow of energy to charge. So our dW dQ gives us our energy. Then our power is the rate of energy with time. So these are the 4 major components of calculations that we should have at our beck and call. For resistance, when we get to Ohm's law, we will be able to tell you how our R, which is the resistance, is equivalent to voltage over current. So I believe I've been able to explain the fundamentals of electricity, which revolves around charge, current, voltage, resistance, and power. So in our next video, we're going to go into the fundamental laws, most especially Ohm's law. So I hope you tune to our channel and stay tuned to our channel so that when those videos are released, you would go ahead to learn more about our Ohm's law. So please feel free to click on the notification icon and subscribe to our YouTube channel for more educative and inciting videos. Thank you.